Okay, so this is experiment 1 for charge tapes. And just a little bit of a roadmap. We have the introduction, data and observations, and measurements taken, and then we're going to talk a little about the closed script Python model. So the experiment involved trying to levitate a piece of charge tape with another piece of charge tape. So they ended up repulsing one another and levitated even though there was still the force of gravity present. And so the couple of the models and fundamental principles is that we're using Newton's second law, F equals ma, and F equals mg, and Coulomb's law in order to properly calculate the charge on each piece of tape. And we can then use stoichiometry and dimensional analysis in order to figure out the total number of charges on a piece of tape. Coulomb's law, which we all know to be F equals kq1 q2 over r squared, and the force due to gravity, which is Fg equals mg. So the model used in the experiment involved 2 charged tapes with one levitating due to the E field created by tape A. And the result of this experiment was the charged piece of tape were found to be positive, the charged piece of tape repulsed each other, and the charge on one piece of tape was turned to be 1.5 e to the negative 8 coulombs, and each tape lost around 9.35 e to the 10 electrons. So the system for this involved the suspended U-tape and the surrounding as well as everything else, including the held U-tape. And the initial conditions is that just simply we prepared 2 charged tapes, and they were both found to have a positive charge. And the reason this was the case is because we saw that these charged tapes, the hanging tape was attracted to the hand, and the hanging tape was attracted to a plastic pen that was rubbed through my hair, which a plastic pen, when rubbed through hair, obtains a negative charge, and if this was attracted, it had to have had a positive charge. And a couple of the necessary assumptions we need to make for the experiment is that both pieces of tape have the same amount of charge, and they act as point charges as opposed to lines of charge, and there's no air resistance to be accounted for, or rather we're choosing to ignore it. And so the procedure for floating the tape is creating 2 U-tapes in the same method described in the previous slides, and then we suspend one of the tapes on objects of equal height, bringing the other tape close to the suspended U-tape until it just barely levitates, and then noting that distance. So here's just a brief free body diagram of the tapes. And then the measurements, we had both the length, the width, the mass, the distance, which is found to be 0.0313. And it's also important to note that the net force on the suspended tape is going to be 0, which is why it is able to float. And this is especially helpful for calculations because we calculated the force of gravity, which is found to be 0.002156. And then we use this and set it equal to the electric force. Assuming both charges were equal, we were able to find the charge to be 1.5 e to the negative 8 coulombs. And then this allowed us to find the number of electrons lost. And then we could also find the area of tape, which then helped us determine the ratio of atoms to deficient electrons, where we found for every 1 deficient electron, there were 4.626 e to the 6 atoms. And so for our coding part 1, here's what I did. There's not much to speak about in terms of this one because it's very similar to experiment 0. And we can see that my diagram depicts the red arrow, which is the force of gravity, green arrow, the electric force because of the repulsion of the like charges, and the charge of the tape was found to be 1.50 e to the negative 8 coulombs. Coding for part 2 is a little bit different because we actually have something interesting. We're treating it as a line of charge instead of a point charge, which is how it's actually supposed to look, which is great, right? And then here's the diagram for it. So we see these white arrows are all these repulsions from, because we're treating it as a line of charge with, in this case, sort of like 10 different points. And we also found the charge to be different. It's like 2.1 e to the negative 9 coulombs. That is much different than our previous value of 1.5 e to the negative 8 coulombs. And there's something to be said about this later in the what if and the why. So a couple sources of error that the charges on the tapes are definitely not equal. It's more than likely not. There were a different number of electrons ripped off. And we treated the lines of charge as point charges in part 1, which is not exactly correct as discussed previously. And just to answer the why question, the line charge Q value is going to be much closer to the real value because it's how it actually exists in nature. There's no such thing as a point charge for a line of tape, but rather it's all of these different charges interacting with one another, which is why a line charge model is so much better. And then for the what if the signs of their charges were reversed, if electrons were positive and protons were negative, we would just be saying that protons were ripped off of the piece of tape instead of electrons. So it really wouldn't make that much of a difference. And just to conclude, modeling a line of charge as a point charge is not very accurate. The humidity of a room definitely can affect the results of the experiment, And calculating charge from the force of gravity of the tape is also slightly inaccurate because we assume the charges were equal. Thank you for listening.